I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on sound waves, harmonics, Doppler effect, and beat frequency. So in this video, we're going to talk about sound waves, harmonics, Doppler effect, and beat frequency. So we've seen this slide before, and we've talked about transverse wave pulses. Now we're going to talk about longitudinal waves, so sound waves. So remember, a longitudinal wave is one where the particles transfer the energy parallel to the direction of the spring. So you can see those coils are compressed. Think of each of those coils like molecules of air traveling and compressing and hitting the next air molecule and so on and so forth, causing the compression wave. Much like you'll see with the tuning fork, when the tuning fork vibrates, you can see it moves the air molecules, and the distance between those dark spots would be the wavelength. Now, if we pause this and we look a little bit deeper into it, the longitudinal mechanical wave or a compression wave. So we have areas of high molecular density, which is the compressions. You can see the dark areas that you have there. And then we also have areas where the density is not as great, called rarefaction. So you can see where the pink arrows are pointing to the spaced out molecules. So sound wave speed can only be changed if something changes about the medium. So the more dense the medium, the faster sound travels because the less distance the particles have to travel. So temperature causes an increase in particle motion, which means they move faster. Pressure means more dense, so it's going to travel faster. And sound travels faster the more dense the medium. And here's some examples of air, water, and glass and the speeds that air travels. Now, the speed of sound in air can be calculated by this equation. So we know the speed of sound in air at 0 degrees Celsius is 331 meters per second. And as the temperature rises or decreases, we multiply by the square root of the temperature in Kelvin divided by 273 Kelvin, which is the 0 degrees Celsius equivalent. So we can calculate the speed, and that's an approximate increase of 0.6 meters per second per degree Celsius. So let's transition to fixed end standing waves or on a string. So in order for a string to produce a standing wave at the correct frequency, it has to have the correct tension. This is why stringed instrument strings need to be tightened or tuned often because the tension decreases as the instrument sits. So we have to tighten it to produce the correct frequency. Now you can see the violin, we have a bow moving across the string. It causes the string to vibrate. You can see the standing wave where we've got an antinode in the middle and a node at each end producing a standing wave. Now the air around the string is compressed and starts the sound traveling through the air. So much like the string just hitting the coils of a slinky, we can see the compression moves through the slinky, and that's what happens with air as the string continues to vibrate back and forth, obviously much faster than we're seeing there. Now, if we look at fixed end standing waves, where we have a node at each end and an antinode in the middle, this is known as the first harmonic. And the first harmonic is half of a wavelength is equal to the length of the string, which means that the wavelength is twice the length of the string. Now, where we have a node in the middle and a node at each end, this is called the second harmonic. And really what would be happening is we're seeing what's in blue on the second half that's vibrating. Now the second harmonic, the wavelength is equal to the length of the string. Then we can also have the third harmonic, and where we have node at each end and two in the middle. And again, we would just be seeing what were in blue on the right. So that's the third harmonic. 3/2 the wavelength is equal to the length, or 2/3 the length is the wavelength. So why are they called harmonics, and what makes them first, second, and third? So what we're going to do is we're going to look at the node-antinode pairings. So we can see node antinode to the middle and antinode node from middle to end. That's the smallest number of node antinode pairs that we can have. So that's called the fundamental frequency. So if we look at the second harmonic and its pairing of node antinodes, what we're going to look at is we're going to count those pairs. So the node antinode node antinode node, we can count the pairs and we can see we have 1, 2, 3, 4, which is a multiple of our first harmonic. So it's twice as great, so that's why it's the second harmonic. We count the third harmonic, we end up with 6 pairs of node antinodes, which is 3 times the amount of node antinode pairings from the first, so that's why it's the third, because it's 3 times. So we're going to transition to closed pipe resonators, one that's opened at one end and closed at the other, which is some organ pipes. So if we look at this tuning fork vibrating back and forth in slow motion, we can see that we have the air molecules create a standing wave inside the pipe. And notice that at the closed end that we have the particles are not moving very much, and at the open end they're moving very rapidly. We also have red dots in the middle. You can see one of the red dots is not moving, so that would be a node. There's no displacement, and the other one's moving much more back and forth, so that would be an antinode. Now, it would be very difficult to draw this standing sound wave. So what we do is we draw it as a transverse wave. And you can see that the red dot that's not moving lines up with a node, and the red dot that's moving back and forth lines up with an antinode. And you can see at one end we have an antinode at the left side, and at the right we have a node. So the particles at the closed end can't move. They get trapped because they can't push the particles in the boundary, so they end up with a node at one end and an antinode at the other. Now, the shortest we can have is a node at one end and an antinode with nothing else in between. So we have node and antinode. So if we draw that as a transverse wave, as we saw with the string, we can see that we have a node at one end and an antinode at the other. An antinode at the open end means that the amplitude is very large, which means that it's a louder sound. So this is the first harmonic with a node and antinode. So it's 1/4 of a wavelength is the length. So that means the wavelength is 4 times the length of the tube. Now, a closed pipe resonator does not produce any even harmonics, only the odd harmonics. We'll explain that in the next slide. So this is the third harmonic, where you have a node and antinode at the end. So the wavelength is 4/3 the length of the closed pipe. And then we produce the fifth harmonic, which means the wavelength is 4/5 the length of the tube. Now, again, we're going to count for the first harmonic our node-antinode pairing, and for the first one, we only have one singular pair, and that's our fundamental frequency, as we know. And then we look at the next harmonic, which we have three pairs, which is 3 times the first harmonic. So that's why it's the third harmonic, because it's 3 times the fundamental frequency. And then the fifth harmonic has 5 pairings of node antinodes, which is why it's the fifth harmonic, because it has 5 times the amount of pairings as the first harmonic. Now we're going to talk about open pipe resonators, and the same thing with the vibrating rod. If you take a metal rod and bang it on the table and it vibrates, this works the same. So this is a pipe with open at both ends. So if we look at the tuning fork in slow motion as it vibrates back and forth, you can see those wave fronts moving, the compression wave, and the compression wave, the distance between those compressions would be the wavelength. So we're going to draw this again as a transverse pulse, and you can see at each end we have an antinode, which means that at each end we're going to be producing the loudest sound because it has the largest amplitude. So if we create a standing wave in an open pipe, this is what it would look like, and it would make a loud sound only when the pipe length was the correct length. So if we look at the lowest number of nodes and antinodes, we have an antinode at each end and a node in the middle, and that's our first harmonic, or our fundamental frequency. So it's going to be the same as a string. 1/2 the wavelength is going to equal the length of the pipe. And then we look at our second harmonic, the wavelength is going to equal the length of the pipe. And then we look at our third harmonic, the 3/2 the wavelength equals the length, or wavelength equals 2/3 the length. And the harmonics are going to be the same. So strings, open pipes, and rods, all harmonics are positive integer multiples of the fundamental frequency. So we can use this equation. The Fn is equal to NF1, F1 being the fundamental frequency and N being the number of harmonics. So if we have the same length pipe or string and we want to play the next harmonic, that's going to be double the frequency. Then the third is triple the frequency, so on and so forth. So closed pipes, the harmonics are only odd positive integer multiples of the fundamental frequency. There are no even multiples of the fundamental harmonic. So we look, F1 is the fundamental frequency, and N is the harmonics, but we only multiply by 1, 3, or 5. So the frequency is going to be the fundamental frequency, then triple that, and then quintuple that, and so on and so forth. So let's look at an example problem. So we have a closed pipe resonator set up using a cylinder of warm water, which would warm the air inside, and a tube is open at both ends placed inside. So it's open at both ends, so it's allowed to fill with water at the one end, So the water cuts it off and closes off the pipe. Now the air temperature inside the tube is warmed to a temperature of 50 degrees Celsius from the warm water, and a tuning fork of 256 hertz is vibrating above the tube. And we want to know what length of the tube above the water has to be if this is going to be the fundamental frequency 256. So let's highlight some information. Air temperature inside is 50 degrees Celsius. Fundamental frequency is 256 hertz. So what we're going to do is we know that the length of the tube for the fundamental frequency of a closed pipe is 1/4 of a wavelength. So we're going to solve for the wavelength. We know wavelength is speed of the sound divided by the frequency, but we don't know the speed or the wavelength. So we can calculate the speed using the equation that speed is equal to 331 meters per second times the square root of the temperature in Kelvin divided by 273 Kelvin. We can substitute in the temperature in Kelvin. 50 degrees is going to be 323 Kelvin. And then when we solve for that, we get 360 meters per second is the speed of sound in the tube. So we can substitute the speed and frequency in and find the wavelength is 1.41 meters. Now we know that the length of the tube is just going to be 1/4 of the wavelength. So we're going to substitute in the wavelength of 1.41 and find that the tube length is 0.35 meters, and that's from the top of the tube just down to the water. So now we're going to transition to something called the Doppler effect. So if we have a bell and we ring the bell, the way the sound travels is outward from the bell, like concentric circles, so it moves outward. So what happens if we take that bell and place it in motion? So it's called the Doppler effect. So I figured let's have Dr. Sheldon Cooper explain to you what the Doppler effect is.
He's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
So if you didn't catch that, I put the text on there. It's the apparent change in frequency of a wave caused by the relative motion between the source of the wave and the observer. So let's look at an example of this. So if we have a plane that's flying, we know it's emitting a sound, and as it flies, you can see that the waves in the front get compressed and the waves behind get stretched out. So if that plane is stationary, we know the sound's going to be concentric circles like the bell was. Now if we look at that a little bit closer, and we see that the wave gets compressed. We have a shorter wavelength in the front and a longer wavelength behind. So we know that wavelength is equal to speed divided by frequency. Now, the speed of a wave, the speed is in air, so we know that there's no change in medium, so that's not going to change the speed. So that leaves us with wavelength and frequency as an inverse relationship. So the shorter the wavelength, the higher the frequency, the longer the wavelength, the lower the frequency. So it sounds something like this using this car horn. So you could hear the frequency or the pitch is higher when it's traveling towards, and when it travels away, the frequency drops quickly to a lower frequency. That's because the waves get compressed as the car travels towards you and stretched out when it is traveling away from you. So you hear a higher frequency traveling towards you and a lower frequency as the car is traveling away from you. Now, the Doppler effect, to calculate the observed frequency, so that's the frequency we heard from the car horn, we can take the source frequency, which is the actual frequency that would be heard if the source was stationary, and we can multiply it by the speed of sound in air in the numerator and denominator. That's the speed at a given temperature. And then we're going to add in the numerator the velocity of the sound observer. So that's if the person that's listening to the sound is moving. And then in the denominator, we're going to subtract the velocity of the source of sound, and those velocities are all in meters per second. And a note, velocity values are positive when objects are moving towards each other and negative when moving away. So if the source moves towards the object or vice versa, or they're both moving towards each other, those values are both positive. If they're both moving away from each other or one's moving away from the other, then those velocities would be negative. Now, if one's moving towards and one's moving away, that means one would have positive value and one would be negative. Now we're going to transition to beat frequency, which is a type of interference effect that results from the superposition of two waves with slightly different frequencies. the waves are periodically in and out of phase, and this causes an alteration between constructive and destructive interference. So what does in phase mean? So if we look at two wave pulses that are in phase, that means their crests and troughs both line up, causing a much larger amplitude wave, and the amplitude of sound is the volume of the sound, so you're going to hear a much louder sound with this constructive interference. When they're out of phase, that means the crests and troughs line up, and that completely cancels out the wave, and this is destructive interference, so you're not going to hear as loud of a sound. It's going to be pretty quiet. So if we look at two waves that are just off their frequencies, you can see that they line up in some places and cancel out in others. So if we look at what the result of that would look like, it would look something like this, where we have out of phase or destructive interference, where you're hearing a quieter sound on the ends, and in the middle, they're in phase, where you're going to be hearing a louder sound. And what that would sound like is something like this. So what you were hearing is two frequencies that were about 4 hertz apart. So to calculate the beat frequency, which is the number of loud, quiet sounds that you hear per second, all we're going to do is we're going to take the absolute value of one of the sounds, and then we're going to subtract the frequency of the similar second sound, and that's going to give us the beat frequency. That's how many loud, quiet times we're going to hear per second. Let's look at another example problem. So we have a violinist tunes their instrument by playing an A4 note, which is 440 hertz, while tuning fork plays another 440 hertz. The violinist walks towards the tuning fork at 1.5 meters per second while continuing to play that note. We want to calculate the beat frequency the violinist hears. So we know that the tuning fork is playing a note of 440 hertz, and the violinist walks towards at 1.5 meters per second. So towards means the wavelengths are going to be shorter, so they're going to hear a higher frequency than 440 from the tuning fork, but they'll hear 440 from the violin. And we're going to assume the speed of sound is in air at room temperatures, 343 meters per second. So the first thing we're going to do is we're going to calculate the observed frequency that's heard from the tuning fork, and we're going to use the Doppler effect equation. The source is not moving, the tuning fork, so we can make that 0. And we can substitute values in for the source, which is the tuning fork is 440. The speed of sound in air at room temperatures, 343 meters per second. Now, because the violinist is walking towards, we know that's going to be a positive value. So that 1.5 meters per second is going to be a positive 1.5 meters per second. And now we can calculate the frequency, which we end up with 441.9 hertz, which we know is correct because it's a higher frequency or higher pitch. So now we know that F1 is 441.9, F2 is 440, that's the violin, the 441 is the tuning fork, and the beat frequency that we're going to hear between them is going to be 441.9 minus 440, which is going to give us a beat frequency of 1.9 hertz, which would sound something like this. So this is an introduction to sound waves, harmonics, Doppler effect, and beat frequency. I hope this was helpful, and I hope you have a great day and even better tomorrow.
If you found this video helpful, click the like button down below, subscribe to my channel, Cabby Coaches, and follow me on Instagram and X at Cabby Coaches.